Midnight in Washington. A clock ticks inside a quiet hallway. Screens glow with a single sentence that says the agency is closed, and outside the planet, Mars turns beneath a sky that is not waiting for anyone. In those same hours, an interstellar visitor slides into its best position for study. Silence meets opportunity, and the timing feels too neat for comfort. Was this nothing more than a bureaucratic pause, or did a rare moment in the cosmos arrive exactly when our public eyes went dim? Stay with me as we pull on this thread and see what unravels. The first fact is not mysterious at all. On the 1st of October 2025, the United States government entered a funding lapse. NASA followed the law that binds every federal agency, pausing most public communications and non-essential outreach while accepted operations continued to protect life and property. Websites froze on a spare notice. Social feeds fell quiet, press rooms emptied, mission control did not. Spacecraft require care, regardless of politics. People remained on console to keep hardware safe, to check temperatures, voltages, and pointing, to send commands when needed. This split between public silence and operational continuity is routine during a shutdown, yet routine feels uncanny when the sky is offering something you may only witness once. That something had a catalogue label and a personality that story lovers could not resist. C 2025 N1, nicknamed 3-Eye Atlas, the third confirmed interstellar object to enter our neighborhood since modern surveys began, was moving along a path that does not loop back. Its orbit is hyperbolic, which is a clinical way of saying it came from the space between stars. It will taste sunlight for a brief season, then it will leave and not return. Interstellar visitors are rare in our experience, and they invite a simple test of our preparedness. Do we notice? Do we coordinate? Do we learn as much as possible before the moment is gone? Geometry made the test harder on Earth exactly, when the shutdown made it harder on trust. In the first week of October, the object sat in a part of the sky near the sun from our vantage point. Observers call this low solar elongation. Imagine trying to study a faint smudge next to a spotlight. Caution and physics discourage reckless pointing. Many ground-based telescopes either could not aim or could not get useful data without risking their instruments. Meanwhile, Mars occupied a much better seat. On or near October 3, the object passed roughly 30 million kilometers from the red planet. In human terms, that distance is enormous. In the scale of the solar system, it is an approachable hello. Mars orbiters with cameras and spectrometers were in position to watch brightness and color and time variation from a cleaner angle than anyone on Earth could manage that week. Here is where perception begins to drift. The European Space Agency had already described an observing campaign centered on those dates. Their public channels remained normal. Interviews and notes circulated about goals and challenges, and the simple excitement of seeing an interstellar visitor from another planet's neighborhood. In the United States, by contrast, the public voice was minimal by policy. Nothing had to be hidden for silence to descend. Silence arrives on its own when the law says it must. Still, silence during a rare event behaves like a vacuum, and a vacuum loves to pull in story. The human mind is a pattern seeker. Give it midnight, a closed homepage, and a sky event with a countdown, and the mind begins to write a script before any data can speak. We can keep two truths in view without forcing them to collide. Truth 1. The shutdown paused public-facing activities that normally turn raw telemetry into widely shared pictures and plain language updates. Truth 2. The timing overlapped with an unusual opportunity at Mars that naturally raised public expectations. Neither truth requires malice. Together they manufacture a mood. The mood is what we feel when an elevator stops between floors for a few seconds longer than expected. Nothing is wrong, yet everything feels like it could be. A responsible investigation starts with the most basic inventory. What exactly stops during a funding lapse, and what continues? Which systems keep receiving data? Which instrument modes are permitted? Which teams remain staffed? Which processes must wait? These questions are not theatrical. They are the rails that keep a narrative from sliding into fantasy. We will walk through that inventory with care, because it tells us what kinds of images or measurements could plausibly exist from the first week of October, what might have been planned before the pause, and what must be processed later, even if it was recorded on time. We will not assert anomalies where a calendar and a policy manual suffice. We will also refuse to ignore places where numbers hint at something interesting, because curiosity is why we build observatories at all. There is another inventory to keep, the sensory one that belongs to cinema. Picture a mission control gallery with fewer chairs filled than usual, soft blue light under quiet screens, a status strip of instruments still reading. Picture Mars as a blood-warm disk crossing black, and beyond it, a thin breath of cometary dust that only reveals itself when geometry is kind. Picture a browser tab that says temporarily unavailable, and a second tab that holds a promised schedule of observations from another agency across an ocean. The tension that results does not prove anything on its own. It does, however, justify patience, and patience is often the only bridge between confusion and understanding. What happens next is not a chase for scandal. It is a step-by-step look at the rules that keep spacecraft alive, the capabilities of the machines that actually could see this object from Mars, and the reasons Earth observers struggled in the same window. It is an honest look at what Hubble already hinted in July about size and activity, and where those early numbers leave uncertainty wide enough for rumor to grow. It is a plan for how we will separate rumor from signal when archives begin to fill again. If the story turns out to be ordinary, we will say so and mean it. If the story contains a real surprise, it will leave footprints that do not vanish when the lights come back on. When a funding lapse hits, the first thing that changes is not the spacecraft. It is the people around them. Federal law forbids spending money that has not been appropriated, so managers separate work into two buckets. One bucket is accepted operations, anything necessary to protect life and property. The other bucket is everything else, including public communication and most science support. That single split produces the strange quiet that follows a shutdown. Screens still glow in control rooms. Telemetry still streams through ground stations. Commands still flow when safety demands them. The outward story, the images, the press notes, and the social posts waits in a queue that no one is allowed to touch. Imagine the layers of a mission as an onion. At the core sits flight software and the bus that keeps a spacecraft alive. Thermal control, power management, reaction wheels or thrusters, radio links, and guidance keep time with their silent metronomes. Around that core sits the operations team, a smaller roster than usual, focused on health and safety. These people watch status strips and voice loops at all hours. They load time-tagged commands for momentum dumps and attitude resets. They run collision avoidance and safe mode recovery drills because hardware does not care about politics. Around that layer sits the science planning machine, target selection meetings, instrument calibration uploads, campaign design. During a shutdown, much of this outer layer slows or stops, unless a direct tie to asset protection can be shown. The outermost skin is public affairs, the writers and producers who translate hard data into a narrative for the rest of us. That layer goes dark first. The ground network that carries bits from deep space continues because it is part of protecting property. Antennas do not sit idle when a spacecraft is passing over the horizon. If an orbiter needs a check that its batteries are not drifting or that a star tracker is behaving, the pass happens. The flow of raw packets into secure storage continues. What pauses is the conversion of those packets into calibrated products and the redistribution to public servers. Even when instruments keep collecting, the pipeline that turns exposure numbers into a clean image can be stuck at step 1. This is why a website can feel frozen while the spacecraft is very much alive. Science teams feel the pause in subtler ways. Many are furloughed. Those who remain on call are asked to focus on safety and on duties defined as essential. A spectrometer might be left in a safe default mode rather than switch through a sequence of filters for a special observation. A camera might hold to a pre-planned cadence rather than pivot to a target of opportunity. None of this signals a cover. It signals caution and compliance. The result is a smaller set of data and a longer delay before anyone outside a small circle can see it. There is also the matter of configuration control and approvals. Even in normal times, changing a spacecraft plan requires steps that show who requested what and when, who checked the pointing limits, and who signed off on risk. During a shutdown, the number of people available to sign is lower, and the tolerance for anything extra is lower still. If a Mars orbiter was going to turn slightly to measure a faint object far from the planet, that turn would need justification that survives a conservative review. If the same measurement could be postponed without risk to the vehicle, the safe choice is often to wait. Public communication is the part everyone notices. Websites and social channels are staffed by people, and those people are asked to stop work. The words "currently closed due to a lapse in government funding" appear, and nothing follows them until the law changes. That silence is not designed to hide science. It is the legal default when appropriations expire. The consequence is unfortunate during rare events. An absence of context leaves room for stories to bloom that have nothing to do with reality on the loop in mission control. Despite the pause, the flight controllers carry a quiet burden. If anything threatens the spacecraft, they act. If a thermal limit creeps high during a long eclipse, they act. If a plasma environment spikes and an instrument needs to safe, they act. These are the boundaries of accepted operations. Within those lines, data can be taken, stored, and later delivered. Outside those lines, most creative planning waits. This means the record of the first week of October will exist in some form if instruments were running, and that record will tell a story when it is finally processed. It may be sparse, it may be ordinary, it will be real. The best way to think about a shutdown is as a mute button, not a power switch. The sound drops away while the orchestra keeps playing behind glass. When the button lifts, the audio returns, sometimes a little out of sync, sometimes needing a bar to catch up. Our task is to remember that quiet does not equal empty. Next, we will meet the visitor that crossed the stage while the volume was low, and see why its path was always going to give Mars the better seat for that brief and precious week. Begin with a line in a star chart that does not close. Most objects we know trace ovals around the Sun, tight like the paths of planets or stretched like the paths of comets, but still they close. C, 2025, N1, does not. Its trajectory opens outward, a clean curve that never returns. Astronomers call that a hyperbola, which is another way of saying this traveller was not born here. It crossed the border of our system without asking permission, and it will leave the same way, a brief guest who refuses a chair. That simple geometry carries a feeling that statistics cannot deliver. When a thing arrives from between stars, you are not just observing a comet, you are reading a message about the larger galaxy, about how other places shed fragments that wander for eons. We have seen this pattern only twice in the modern era. In 2017, a thin object that reflected sunlight strangely passed close to the Sun and then away. It did not show a clear plume of gas, yet it behaved as if something gentle pushed on it. Debate followed, some of it technical, some of it theatrical, and the lesson was that the sky can produce puzzles faster than consensus can form. In 2019, another visitor appeared, brighter and easier to classify. It released gas like a familiar comet, and its spectrum looked like ordinary chemistry. That second case calmed nerves and set a baseline. This third one arrives into that history, and the comparison sharpens our questions. Are we looking at a normal comet from another system, or a cousin with a few traits we did not predict? To understand what was possible to see in early October, picture the object as a nucleus too small to resolve, wrapped in a coma that sunlight lifts grain by grain from its surface. Cameras that are far away do not sketch a face. They measure broad brightness and how that brightness changes across time and color. Those signs can reveal rotation, they can hint at shape, they can show whether one side of the body vents more than another, but none of it produces a postcard. The power of that information is not in spectacle. It is in pattern. A steady rhythm implies a tumbling form. A sudden spike implies a surface patch that woke up, or a fragment that split free. The path through our neighborhood also sets a tempo. The object does not linger near the Sunday. It dives inward, then swings around and climbs back into the dark. That means opportunities are narrow. Observations must stack up in a short window to build a coherent story. If one vantage point is compromised by glare, another vantage point can take the lead. This is why the geometry of that first week matters. As Earth looked into bright sky, Mars sat at an angle where the line from orbiter to object crossed less scattered light. From there, brightness against black is a cleaner measure, and faint changes are easier to track. There is a second reason. The third interstellar visitor invites special care. Each new case updates our sense of the population beyond the heliosphere. If every visitor looks like a comet, then disks around other stars must send out many icy fragments. If a visitor looks dense or behaves in ways that stretch comet physics, then the variety of building blocks in other systems might be richer than models assume. None of those inferences require exotic explanations. They do require careful fits to the orbit and cross-checks on spectra and light curves once they are available, and they require that we avoid leaping from uncertainty to drama. Wonder can share the frame with restraint. The name itself carries a small story. Surveys scan the sky each night. They subtract one frame from the next. They flag anything that moves. Most flagged points are familiar near-Earth objects, or long-period comets that return after many centuries. A few points refuse the usual fits. They do not bend enough under the sunday. Follow-up measurements stack into an answer. The eccentricity rises above 1, which is the threshold for an open curve. The registry adds a third interstellar number. The community takes notice. Proposals are drafted, observatories negotiate for time, and the clock begins to run. What is known at this point can be stated simply. The trajectory is open. The object is active enough to carry a coma. The best early images could not isolate the solid core, which leaves size and mass, uncertain by a wide range. Those facts are not disappointing. They are the scaffolding for the rest of the inquiry. The unknowns are equally clear. We do not yet know the precise density. We do not yet know whether its gases follow the familiar recipe of water and carbon-bearing molecules, or if another volatile dominates. We do not yet know whether its rotation is simple or chaotic. Every one of those questions can be tested with time series data and spectra. When a traveler comes from the space between stars, the right posture is attention, not alarm. We collect what is possible from the vantage we have. We compare with the 2 prior cases. We store the data with care. The rest of this story will follow the path of that discipline. Next, we will ask why Mars offered the better angle that week, and how that advantage turned a distant orbiter into our most practical seat at the show. We are still following the same question. What was ordinary procedure, and what hints at something truly unusual? Begin with a picture you can hold in your head. Place the Sun at the center, set Earth on one side, set Mars farther around its path, and lay the traveler on a line that sweeps inward then out. From Earth during that first week of October, the object hugged the Sun in our sky. Observers call this low elongation. The angle between the object and the Sun as seen from here was small. A small angle means glare, scattered light, and risk to optics if you point too near the star that powers everything. From Mars, the angle opened wider. The comet stood farther from the Sun on that sky, so a camera looking out from Mars saw more black around the faint smear and less whitewash around it. That alone can turn a borderline target into a workable one. Distance helps too, but in a counterintuitive way. The comet was roughly 30 million kilometers from Mars around October 3. That is far beyond intimate detail. No orbiter could draw a sharp nucleus at that range. Yet distance combined with geometry can improve the contrast between target and background. Think of a lamppost on a foggy night. Look from a place where mist fills your line of sight, and the scene becomes soup. Step a block to the side. The light remains the same. The fog thins, and shapes separate. Mars had the sidestep. The orbiter did not have to lift a veil so bright that it crushed the signal before it reached the detector. The instruments circling Mars were not designed for celebrity shots of a passing interstellar body. They were built to study the planet below, to read its atmosphere, to map its surface, to watch dust and trace gases and plasma. Even so, many carry cameras with multiple filters and spectrometers that can see light split by wavelength. At tens of millions of kilometers, those tools do their work through time rather than resolution. They measure how total brightness changes over an hour or a night. They sample color to infer which molecules fluoresce under sunlight. They look for asymmetries in the coma that betray a jet that is slightly stronger on one side. If the nucleus rotates, a periodic rise and fall appears in the light curve. If an outburst occurs, a sudden jump appears and decays. None of this gives you a face. All of it gives you behavior. Timing also favored Mars. A spacecraft in orbit has regular communication passes, predictable windows when data rides a radio beam to a dish on Earth. Those windows do not require press staff. They do not require a social post. They exist as part of protecting property, so they persist in a funding lapse. That means a log of what instruments did during the Mars window will exist, even if it takes weeks to calibrate and publish. An investigator can match timestamps to the geometry and see whether the opportunities were seized. A scientist can fold those same times into a rotation model and ask whether peaks line up from one day to the next. The view from Earth was not only bright, it was also short. Twilight gives you a sliver of safe pointing when the Sun sits just below the horizon. If a target is close to the Sun, its altitude is low, the air is thick, and the chance of cloud and haze grows. Observers weigh risk against reward and often choose to wait rather than push hardware near limits for a faint prize. The decision is not a lack of interest. It is stewardship. From Mars, the prize was better placed in the sky. The error in that calculation is none at all. The only limits are spacecraft safety, instrument temperature, pointing constraints, and time. A useful way to judge what Mars could do is to set expectations soberly. At 30 million kilometers, a pixel can span tens of kilometers depending on optics and distance. There is no hope of measuring shape directly. There is hope of measuring the way light rises and falls, which, when plotted across hours and days, becomes a fingerprint of rotation and activity. There is hope of low-resolution spectra that show common gases and dust. There is hope of aligning those measurements with the best ground-based photometry taken before and after the glare period, so that the whole curve of behavior is stitched from multiple vantage points into a coherent story. It is tempting to turn an observing advantage into an expectation of revelation. The better story is simpler. Mars had the cleaner angle, so Mars had the best chance to gather modest but meaningful traces during a narrow week when Earth was largely blind. That advantage does not imply drama, it implies opportunity. If the comet behaved like a comet, Mars-based measurements will show that calmly. If something unusual happened, the signatures will be there too, small but persistent, waiting to be compared against models when the archives open again. The result of this geometry is a kind of relay. Earth hands the baton to Mars for a few days, then Mars hands it back when the object swings behind the Sun and later reappears into darker morning skies. A relay only works if you know who carries the baton at each leg. Next, we will name the orbiters above the red planet and ask what each could contribute, so that expectations for data match the tools that were actually in play. Start with a roster, not of heroes, but of instruments built for patience. Above Mars there is a small city of machines. Each one carries sensors tuned to the planet below, yet each one can spare a glance for a visitor in the dark when geometry smiles. To understand what might have been measured during the first week of October, we need to meet these machines as they are, not as we wish they were. Mars Express is the veteran. It has circled the planet since the early 2000s. Its camera suite can produce wide coverage and stereo views of terrain, which also means it can aim off the limb and record faint structures against black space. Think of it as a steady painter with broad brushes. At tens of millions of kilometers, Mars Express cannot resolve a nucleus, yet it can gather photometry, total light in chosen filters, and repeat that measure in sequences that capture variation with time. Those sequences are the raw material for a light curve. If the traveler rotates and its coma is not perfectly symmetric, a rise and fall emerges. That rhythm is evidence even when no detail is seen. The Trace Gas Orbiter carries instruments with a taste for spectra. Its primary mission is to analyze the Martian atmosphere, to hunt for faint signatures that whisper through sunlight as it passes a thin sky. Those same spectrometers can stare outward and integrate on a point that drifts slowly relative to star fields. With enough dwell time, they can separate brightness into colors that correspond to common cometary gases and dust. Water-related bands, carbon-bearing lines, possibly weak metal lines that appear when grains heat and shed atoms. At this distance, the result is not a detailed chemical portrait. It is a set of clues that cross-check groundwork done earlier and work planned for later. Confirmed presence or absence of a few species can change the story from speculation to a bounded set of possibilities. On the American side, the Mars Reconnaissance Orbiter is the sharp-eyed scout of surfaces. Its famous camera can pick out objects the size of a desk on the ground. A camera like that has a small field and it reaches its sharpness by being close to its subject. At 30 million kilometers, that sharpness dissolves into coarse sampling. Yet even a narrow camera can be commanded to take exposures of a faint target for the sake of brightness over time. There is also the value of color filters. A small stack of frames through different bands can reveal whether the coma is bluer or redder than nearby sky. That shift may indicate dust size changes or a jet that introduces asymmetry. MAVEN watches the space around Mars. It listens to plasma. It reads energetic particles. It tastes the electric and magnetic weather that flows from the Sunday. While MAVEN was not built to look at a comet, it provides context for anything the comet might experience at that time. If the solar wind grew rough during the week, a temporary brightening seen by a camera might be a reaction to that change rather than a mystery. If conditions were quiet, a change in the coma would call for a different explanation. Context is not decoration. It is a way to rule out simple causes before we entertain complex ones. There are also surface assets that sometimes surprise us with skyward work. Curiosity and Perseverance are geologists on wheels. Their hazard cameras and navigation cameras can, if commanded, capture the sky. A bright comet under perfect geometry can leave a trace in such images. During the Mars window for this object, brightness and distance make such a capture unlikely, yet the concept is worth keeping in mind. The surface can contribute timing, even if only as an upper limit, by showing nothing when something brighter would have been seen. Every spacecraft operates within rules. There are sun avoidance angles, heater limits, momentum budgets, and schedules that must weave through ground station availability. During a funding lapse, those rules are followed with even more caution than usual. That does not mean no data were taken. It means that data were taken when they fit inside careful plans. The European teams had listed their intent publicly before the week began. That plan likely guided how often and how long instruments stared into the dark. American plans were not described in public during the pause, yet the hardware continued to orbit on time, which means logs exist that can later be matched to opportunity. Expectation management is the key that unlocks honest excitement. None of these orbiters could snap a clean portrait of a nucleus at 30 million kilometers. All of them could contribute to a composite understanding that is stronger than any one measurement. Wide-field imaging can show whether the coma is smooth or slightly lopsided. Time series data can reveal rotation through a regular brightening and dimming. Simple spectra can show which molecules glow and how strongly, which feeds into mass loss estimates. Plasma context can help explain momentary changes that do not repeat. The fleet is not a single instrument, it is an orchestra. During the first week of October, the orchestra had fewer people at the mixing board and fewer press notes making their way to the audience. The players still held their parts. The score was modest, but real. When the recordings are released, perhaps slowly, they will layer into a sound that says something about how an interstellar object behaved when Mars had the angle and Earth had the glare. Now that we have met the instruments and set sensible limits, we can turn back toward our own planet and ask why ground-based telescopes struggled in the same days, and how that struggle amplified the feeling that someone turned down the volume on purpose. If the sky is a stage, October began with the spotlight pointed straight into our eyes. From Earth, the object sat near the sun in the morning sky. Astronomers describe that angle as solar elongation. When elongation is small, brightness from the sun bleeds across the field. Scattered light lifts the background. Detectors see a grey wash where they usually see black. Even experienced observers become cautious. Point too near the sun and you can damage a camera, a mirror, or the thin coatings that make precision optics sing. On paper, the comet was there. In practice, it hid inside the halo of the star that keeps us alive. Twilight complicates everything. The safe time to look near the sun is when the sun itself is just below the horizon. That gives a sliver of darkness while the target remains above the skyline. The air is thickest then. Light passes through a heavy air mass and picks up color and blur. Ridges or buildings cut the already small window. Weather doubles the trouble. A single bank of high haze can erase an hour of planning. On a perfect morning, a few frames might be banked. On a typical morning, the reward does not justify the risk or the cost in staff hours when conditions turn marginal at the last minute. Some telescopes are designed to cope with harsh conditions. Coronagraphs and solar observers learn to tame the glare by blocking the sun itself and shaping scattered light. Their instruments are precious and their rules strict. A target that sits a few degrees from the sun is not a casual tasking. Safety margins exist for reasons written in fire. Even at nighttime, observatories, the teams who point large mirrors treat sun avoidance as a sacred checklist. Minimum angles are enforced. Supervisors sign off. The culture is conservative by design, because the replacement cost of a damaged instrument is measured in years, and the loss to the field is larger still. There is also the human rhythm of observatories to consider. Schedules are written months ahead. Operators sleep according to the night. Proposals are graded by committees that weigh science against risk. A target of opportunity can cut the line if it is both safe and compelling. During a week when the sun sits too close, that second condition cannot outweigh the first. Stewardship is part of science. Choosing not to look can be the correct choice when the price of a mistake is high and the likely data are thin. The physics of the atmosphere does not help. Low-altitude targets suffer from turbulence that smears fine detail into a soft smear. Astronomers call this poor seeing. Even if a detector is safe, long exposures pick up more glow than signal. Sky brightness climbs quickly just before sunrise. Read noise and photon noise add together, and the faint blur of a small coma sinks into the noise floor. Stacking many exposures can recover a trace, but only if each exposure clears a threshold of quality. Many will not. Those that do may still fall below the standards needed for solid photometry. That is why professional teams often defer to space-based assets when elongation is small. A spacecraft above the atmosphere can collect longer integrations without the veil of air. A platform at Mars can see a wider angle from the Sun than Earth can at that moment. The handoff is pragmatic rather than romantic. It is about maximizing the odds that a modest measurement is achieved somewhere, rather than a poor one is forced everywhere. In early October, that handoff made sense. The red planet had the cleaner line of sight, so its orbiters became the primary witnesses for a few days. None of this signals indifference on the ground. Observatories still pointed when geometry allowed. Some high-altitude sites attempted twilight searches. Amateur observers with smaller instruments and flexible routines tried as well. Their efforts matter because they extend the time series on both sides of the glare period. Even a non-detection can be valuable. It sets an upper limit on brightness that helps pin down activity models later. A careful negative result is a contribution, not a failure. Public perception rarely sees any of this calculus. Viewers see a frozen website and assume the sky fell quiet. The sky did not. The geometry made Earth a poor vantage for a week. At the same time, policy muted the public voice of the largest American agency. Those two facts reinforced each other in unhelpful ways. When one channel goes dim, another needs to be loud to keep context intact. Europe filled part of that gap. Mars filled another. Earth-based measurements would resume when the object moved away from the sun in our sky, and the air once again became more friend than foe. There was one earlier look that framed expectations. In July, a space telescope with stable optics and dark skies recorded the visitor when elongation was kinder. Those images set the baseline that guides interpretation. They showed activity without detail, and they left size and mass loose. That looseness is not a flaw. It is an honest statement about the limits of early data. It is also the right bridge to our next question. What did those July images truly reveal, and what did they leave open wide enough for rumors to walk through? Begin with a quiet instrument that reads light like a monk reading a manuscript. In July, when the sun sat at a kinder angle and the sky around the target was darker, the space telescope turned its eye and gathered deep exposures of C2025 N1. The frames do not show a solid body. They show a condensed glow that swells outward, brightest in the center and fading through the wings. That glow is the coma, dust, and gas lifted from a nucleus too small and distant to resolve. Astronomers treat the glow as a clue. They measure how brightness falls with distance from the center. They compare that curve to models of dust production and scattering. From this comparison, they infer a range of possible nucleus sizes and activity levels. The result is not a single number, it is a bracket. Inside that bracket lives both caution and intrigue. If the nucleus is small and the dust output modest, the total mass can be ordinary for a comet. If the nucleus is larger and still looks faint, then albedo and dust physics come into play. A dark surface reflects less, so it can hide more bulk inside the same envelope of light. None of those possibilities require anything exotic. They do require patience and follow-up to tighten the range. July gave the first stakes in the ground. Early October would have added new stakes from a different angle if everything went smoothly. The gap between those months is where uncertainty does its best work, because people love to sprint from a bracket to a conclusion. The July spectra added a second strand of information. By splitting light into wavelengths, the telescope can look for signatures that belong to common molecules and atoms. Water-related fragments often show their presence. Carbon-bearing molecules too. In some cases, metals like nickel and iron appear in faint lines when dust grains release atoms under heating. These appearances are not dramatic by themselves. Metals have been seen in other comets, including many from our own system. Strength of lines matters. Context matters. A line that is a little stronger than average can be a result of viewing geometry or grain size distribution. A line that is wildly out of family might be an early flag for something unusual. July did not deliver a wild flag. It delivered the modest palette that tells us we are looking at a cometary environment rather than an inert rock. There is also the matter of motion. A series of images across a night can measure a small shift in the center of brightness or a change in the overall light as the body rotates. Stack enough nights and you can tease out a period or at least a pattern. July gave hints, but not a full rhythm. The object was distant and faint. Noise lives in that region, and it asks for mercy. The way you grant that mercy is by adding time. More nights from a different vantage improve the chance of extracting a spin, or of discovering that the spin is complex in a way that blurs a clean signal. What Hubble could not do is as important as what it did. It could not resolve the nucleus to measure shape directly. It could not weigh the object. It could not by itself prove that any specific molecule dominates the coma unless the signal rose above strict thresholds. It could not foretell whether the object would brighten gently toward perihelion or surprise with an outburst. These are not shortcomings, they are boundaries. Science gains power by acknowledging boundaries before beginning to speculate on what might live beyond them. This is where expectations should be tuned. July set a baseline. The object appears cometary. The size range is wide. The mass estimate inherits that width. The spectrum does not demand an exotic interpretation. The light curve is still a sketch. If nothing strange happens, later observations should tighten each of these threads into a cleaner rope. If something does happen, the rope will kink in ways that anyone can see once the data flow resumes. Either way, the July frames are the control image, the before picture that every after picture will meet in a fair comparison. When public communication quieted in early October, these July results became the only clear reference for non-specialists. Without new releases to anchor discussion, the unavoidable uncertainty in size and mass turned into a fertile field for confident claims. Some voices pointed at an upper bound as if it were the number. Others took talk of metals as if it meant fabrication rather than dust chemistry. The correct antidote is not scolding. It is more data with timestamps and modes and independent confirmation. The antidote arrives when archives open and the week that followed is visible at last, which takes us to the 7 days that mattered most for perception. A short span in which Earth looked into glare, Mars had the advantage, and the largest American public megaphone was legally paused. In that span, the empty air between what was happening and what was being said filled with rumor and with sincere questions. Next, we will enter that dead zone, not to dramatize it, but to sort what must be silenced by policy from what would count as a real gap that deserves a second and third look when the lights come on again. Call it a hinge in the timeline. From October 1 through October 7, a rare visitor passed through the best Martian geometry, while the largest American space agency kept its public voice on mute. The screen most people check first displayed a single line that the agency was closed. European feeds continued as usual. The gap between those two experiences shaped everything that followed. It is tempting to give that gap a sinister name. Better to start with a simple question. What would ordinary silence look like? And what would a real anomaly look like once the data finally move from closed rooms to public servers? Ordinary silence wears familiar clothes. Mission homepages stop refreshing their carousels. The image of the day holds position. Social accounts post nothing. Raw image browsers that usually tick forward in near real time freeze at a pre-shutdown timestamp. None of this implies that instruments stopped collecting telemetry. It implies that the staff who would clean, label, and publish the telemetry are not at their desks. This version of silence leaves a paper trail that anyone can predict. Continuity plans say in plain language that non-essential communication halts during a lapse. If you see static displays that match the plan, you are seeing bureaucracy behave as designed. A real anomaly would leave different fingerprints. Imagine a previously announced observation window that later produces no products at all when publication resumes, with no explanation in the logs, and with no corresponding housekeeping records to show that the instruments were offline. Imagine a set of files that appear briefly, then disappear, and later reappear with altered metadata that breaks checksum history. Imagine a scheduled spacecraft maneuver that shows up in tracking data, but not in operations notes, or the reverse. Those patterns are not the same as a quiet homepage. They ask for follow-up questions with names and times attached. The first week of October created room for both readings because verification was delayed by design. During those 7 days, private channels still carried traffic. Commands were uplinked within the rules of safety. Health data came down through deep space antennas and landed on secure storage. The queue built. Nothing in that flow resolves the public perception problem in the moment. People outside the small circle cannot know what was recorded until archives open and teams return to clear the backlog. That delay is where rumor thrives. Anonymous posts fill the vacuum with claims of pulled frames and mystery burns. Some are made in bad faith. Many are made in good faith by people who have not seen how slow raw data becomes a finished product. Another ingredient made the week feel stranger than it was. Europe had set expectations before the window opened. Interviews with scientists described intent to turn instruments outward and try for photometry in simple spectra. That transparency established a living rhythm for audiences who follow space news. When one voice in the band stops and another keeps playing, the ear hears dissonance. Dissonance is not proof, it is a feeling. Feelings are powerful, and in the age of instant sharing they spread quickly, turning questions into stories before the first calibration file exists. There is a reason to name the dead zone with care. The phrase can turn into a character of its own, a shadow that people project meaning onto long after the window closes. A calmer frame is to call it a documentation gap. The events of those 7 days will be documented when people return to work and publish logs and products. The question then becomes simple. Do the logs match the geometry? Do the timestamps match the opportunities? Do the instrument modes match plausible plans? Does anything in the housekeeping suggest outages or safing that explain missing data? If there was a burst of activity in a light curve, does it line up with a spike in space weather? If there was an outburst claim in a forum, does any independent observer record a similar change in brightness? It helps to prepare a basic checklist in advance, so that when archives open, the investigation does not depend on memory and emotion. First, list the announced European observations and their timing. Second, watch for the corresponding files in their public repositories. Third, for Mars orbiters operated by the United States, look for later additions that carry timestamps inside the window. Even a minimal entry with a mode flag tells you the instrument was pointed and collecting. Fourth, compare all of that to independent astrometry gathered by amateurs and by ground-based surveys on either side of the glare period. The orbit should fit across sources, not perfectly, but within sensible residuals that fall as more data are added. If this sounds procedural, that is the point. A week of silence does not demand drama if process can test claims with simple anchors. When the pages begin to update again, anyone can sit with a cup of coffee and match times to plans. If the matches are clean, the dead zone becomes a footnote. If they are not, you will know where to ask for clarification. Agencies are imperfect. People make mistakes. Files get mislabeled and then fixed. Documentation tells that story too. It is better to follow the path of receipts than to build a tower of conjecture. The dead zone was not a void in space. Mars still orbited. The visitor still moved. Instruments still saw if they were allowed to see. The void lived in our feeds and in our heads, a human absence that invites narrative. We can respect the feeling without being ruled by it. The next step is to arm ourselves with methods that turn rumor into work. That begins with the orbit, because the orbit is where the math says your story must meet reality. Rumor loves speed. Signal loves patience. In the first week of October, the world had plenty of the former and very little of the latter. If we want a story that survives the restart of normal life, we need a method that is both simple and stubborn. The method begins with time. Time is the spine of every observation. When files appear in archives after a pause, the first question is always the same. Do the timestamps match the windows when geometry said the target was in range? If a European orbiter promised a stare on the 3rd, do we see files recorded on the 3rd? If a Mars orbiter under American control shows entries on the 2nd or the 4th, do those entries line up with pointing that would place the comet inside a sensible field? Time mismatches happen. A clock can drift. A header can be written in one time zone, while a plan was described in another. Those quirks are fixed with footnotes. What cannot be excused is a parade of times that never touch the week that mattered. When time does not touch opportunity, the claim of observation is only a wish. The next layer is instrument mode. Cameras and spectrometers carry their own diary inside the metadata. Each record tells you which filter was in place. It tells you the exposure length. It tells you whether the instrument was in a safe default or in a targeted configuration. If a log says a spectrometer spent 2 hours in a mode designed to look outward at dark sky, that is a real intention. If the same instrument stayed in calibration mode facing the planet limb, then the story shifts. There is no scandal in routine, there is only clarity. A targeted mode during the window means the deliberate attempt to gather comet data. A routine mode means the team stayed conservative. Both outcomes can be understood once the labels are read. Pointing is the third anchor. Spacecraft know where they looked, not perfectly, but with enough precision to say whether a faint object could fall inside the field. Housekeeping files carry quaternions and target coordinates. Plots of boresight against star fields can be reconstructed. When the boresight sweeps near the predicted ephemeris of the comet, we can say the attempt was real. When it does not, the record tells us that other priorities held the schedule. Here again, patience beats suspicion. Plans change. Safe modes interrupt work and leave gaps that look mysterious when stripped of context. The context lives in the housekeeping and in notes that explain why a pass was spent cooling a radiator instead of opening a shutter. Cross-comparison adds backbone to all of this. A single instrument can lie by accident. It can mislabel a header. It can glitch. Two instruments at two agencies rarely lie in the same way at the same time. If an ESA camera reports a faint brightening on the 3rd, and a Mars orbiter reports a subtle rise 1 hour later, the agreement pushes the story toward reality. If a supposed outburst appears in one set only, then replication must be sought. Ground-based observers on the shoulders of the glare period can also help. They can confirm a trend before and after the week, and set upper limits during the worst days. The orbit-fitting community watches all of these numbers and turns them into residuals that either shrink with time or swell under the strain of a bad assumption. Integrity checks keep everyone honest. A simple checksum proves that a file has not been altered since it left the pipeline. Headers tell you who processed the data and which software version was used. Reprocessing is normal and even healthy. When a file is reissued, the version should change and a note should explain what was corrected. Quiet substitution is a red flag. Loud correction is a sign of a culture that expects mistakes and cleans them in public. When rumors claim that frames appeared, then vanished, the way to answer is to look at the file tree and the change logs. If an entry shows removal without explanation, ask for the reason. Lost frames do happen. Disk failures are not myths. The way an archive talks about these events matters as much as the events themselves. There is one more habit that separates rumor from signal. It is the willingness to write down what would count as disproof. If you believe a dramatic maneuver occurred, write the signature that must be present in tracking data to support it. If you believe data were withheld, write the set of files that would have to be missing to make the case. Then check. When the evidence fails to appear, retire the claim with grace. If the evidence does appear, escalate with specifics and with humility. Precision invites respect. Vagueness invites noise. Every 3 parts, let us remember the through line. We are testing a mood created by timing against numbers that do not care about moods. By the time the archives open, this method will feel boring. Good. Boring is what the truth often looks like when it first arrives. A table of times, a list of modes, a few small plots. Boring is also powerful. It lets different teams reproduce each other, and it turns social heat into shared light. The next place to apply this discipline is the orbit itself. The path is where math and measurement meet, and it is the part of the story that can punish a pretty narrative when it strays from reality. We will step there next and see whether the curve bends where rumor expects it to bend, or whether it stays true to the physics we already understand. An orbit is a promise written in gravity and sunlight. It gives you a path that your eyes can follow across the dome of the sky, and a set of numbers that your hands can test at a desk. When an object moves through the inner system, observatories on Earth and in space mark its position against background stars. Each mark is a timestamp and 2 angles. Stack enough marks from different places, and a solution emerges. For a visitor from interstellar space, the solution takes the shape of a hyperbola, eccentricity greater than 1. A swing past the sun and a steady climb back to the deep. The curve does not care about our timing, our press rooms, or our moods. It cares about the pull of the sun, the push of faint jets, and the precision of the people who make the marks. The most honest picture of this process is surprisingly humble. A few points from July, more points from August and September, then a stall while glare and shutdown limit the flow. Later, more points from late November and December, when the object reappears into kinder skies. Software pulls all of these points into a best fit. Residuals show the difference between where the model says the object should be and where it was seen. If residuals drop as new data arrive, the model is winning. If residuals grow, something is missing. That something might be mundane, such as a consistent drift in one observer's clock, or it might be physical, such as a small thrust from outgassing that the simple model did not include. Outgassing can be folded into the math with non-gravitational parameters that stand in for the effect of sun-warmed jets. These parameters are tiny accelerations that point mostly away from the sun, sometimes tilted by the way the nucleus spins. They have names that sound like an engineer's shorthand: a 1, a 2, a 3. They are not magic. They are acknowledgements that ice turns to gas and gas carries momentum. When these terms are added, a curve that was slightly off can fall into place. The data will tell you whether such terms are needed. If the fit is clean without them, the comet was quiet, or the geometry hid the effect. If the fit demands them, the comet was active enough to leave a measurable trace in its path. Here is where rumor often tries to sneak in. A claim that the object made a sudden jump during the first week of October would leave a scar in the orbit fit. A real jump would show up as a set of residuals that flip sign across a short span, or as a change in the fitted velocity that does not match the slow push of gases. Independent observers would feel that scar in their own fits unless they all repeated the same mistake. The safer assumption is that independent people in different places rarely repeat the same mistake in the same way. This is why the orbit is a harsh judge of stories. It aggregates many hands into one curve and refuses to indulge a plot twist that is not present in the points. There is also the appeal of Doppler drift for anyone listening with a spectrograph. Light from the coma carries lines that shift slightly as the object moves toward or away from the observer. Those shifts are predictable once the orbit is known. If an anomaly were present during the dead zone, the drift would misbehave in a way that does not match the ephemeris. Checking this is not glamorous. It is a matter of plotting measured line centers against time and comparing to the expected slope. If the slopes agree, the story stays calm. If they do not, the discrepancy must repeat across instruments before it graduates from curiosity to claim. A small caution belongs here. The best fits are only as good as the arc of data they include. A short arc can produce an orbit that looks convincing for a while, then drifts when new points arrive. That is why early talk about eccentricity and non-grav terms carries wide error bars, and why confidence grows only when the calendar adds nights. By the time December measurements come in, the arc will be long enough to punish wrong assumptions and reward models that respected the uncertainties. Every 3 parts, let us restate the through line. We are balancing spectacle with receipts, and the receipts start with where the object actually was. If the comet behaved like a comet, the orbit will say so without fuss. The points will fall near the line. The required non-grav terms will be small and sensible. If something odd happened during the week of silence, the orbit will whisper it through residuals that refuse to shrink, or through a slope that refuses to match. Either way, the path disciplines our imagination. With that discipline in place, we can look more closely at the tiny forces that shape a comet's journey, and see how sunlight can become a thruster made of vapor and dust. Imagine a lump of ancient snow and stone drifting where sunlight is thin as memory. As the visitor approaches the inner system, that light grows warm enough to change the physics at the surface. Ice turns to gas. Gas finds cracks and vents. The flow carries dust grains and creates a haze that we call a coma. Momentum is conserved, so a puff that leaves the nucleus pushes back on the body itself. The thrust is tiny, but it acts for hours and days. Over time, tiny is enough. A path that once matched pure gravity begins to curve by a whisper. That whisper is measurable if you watch long enough and fit the motion with care. Comet jets are not fire hoses. They are patchy, fickle, and often tied to sunlight angles on facets of an irregular shape. If a jet turns on when a certain face rolls into dawn, the total brightness rises and falls with a tempo that follows the spin. This is why observers chase light curves. The pattern of brightening and dimming across a night is a secret telling. You can infer rotation rate. You can infer whether one hemisphere is more awake than the other. In some cases, you can even infer that the rotation is not simple, that it wobbles slightly because the mass distribution is uneven. None of this requires seeing the body itself. The coma is a billboard that advertises the engine within. Physics gives a way to fold these ideas into the orbit. the solution without getting lost in details that no camera can resolve. Astronomers introduced three small terms that represent forces along three axes relative to the Sun and the object's velocity. The math is not romantic. It is the gentlest possible correction to a gravitational path. You can think of it as permission for sunlight and vapor to tug a little. When the fit improves, the permission was wise. When the fit does not improve, the object was quiet, or the data were not sensitive enough to feel the push. There is also a seasonal effect, a word that sounds strange for a body that crosses our view so quickly. As the distance to the Sun changes, the surface warms or cools, and the rate of gas production follows. Some patches of volatile material wake only when heated past a threshold, then they surge and relax. If an outburst occurred near the Mars window, that event would show up as a spike in brightness in any time series gathered from orbit. It would also show as a change in the non-grav terms if the surge lasted long enough to matter for motion. A single night of flurry can make a beautiful light curve and leave almost no trace in the path. A week of elevated activity can do both. The plasma around a comet matters as well. The solar wind is a river of charged particles that blows outward at hundreds of kilometers per second. When that river thickens or carries a shock from a solar eruption, it can sweep a comet tail into a kink or enhance ion emission. Instruments like those on MAVEN record such changes above Mars. If a brightness event aligns with a recorded change in solar wind conditions, a simple explanation suggests itself. The visitor got slapped by weather. The glow was a response to environment, not a signal of machinery. Skepticism asks whether all this talk of tiny thrusters can be stretched too far, whether people use it to explain away any discrepancy they do not like. The counter is straightforward. The parameters that represent these forces are not free to wander without consequence. They must be physically sensible and remain consistent with the observed brightness and the expected gas production rates for a body of the inferred size. If a fit demands a push that would require absurd mass loss, the model is wrong. If a light curve shows no sign of activity, but the orbit screams of thrust, the model is wrong. Cross-checks keep everyone honest. Photometry talks to astrometry. Spectra talk to both. There is a quieter lesson in these tiny forces. They remind us that a comet is not a passive rock. It is a machine powered by sunlight and shaped by its own fractures and grains. When we imagine dramatic maneuvers during the week of silence, we must remember that nature already performs a slow dance that looks like intention if you squint. A rising jet can rotate a body by small amounts over months. A shifting patch can modulate the light in ways that feel like code to anyone eager for a message. The right response to that feeling is not dismissal, it is calibration. Measure first, marvel second. Every three parts let us rest our eyes on the through line. Known forces first, unknowns must earn their place. With that ethic in hand, the next curiosity comes into focus. The word metal has already made a cameo in public conversations. Some spectra in some comets carry faint lines from nickel and iron. What does that really mean here? Does metal in a mist suggest an alien origin, or does it simply tell a story about dust grains warmed by a star? We will walk that edge next, with examples that keep wonder and restraint on speaking terms. Say the word metal and imaginations wake up. A comet that carries hints of nickel or iron sounds like a story about industry, about something forged. The reality inside a spectrum is gentler. When sunlight heats dust grains, atoms can drift off those grains and leave faint lines in the light. Observers have seen such lines in many comets from our own system. They are not neon, signs for technology. They are signatures of geology and chemistry that began in the cold workshops where small bodies formed. To grasp this, picture a dust grain as a tiny layered world. Silicates and carbon-bearing compounds, traces of metals bound in minerals, perhaps ice that holds volatile molecules. When the grain is lifted into the coma, it begins to warm and to collide with photons and particles. Some bonds loosen, a few atoms escape, and those atoms emit or absorb light at very specific colors. A spectrometer records those colors as thin lines against a gray field. Nickel can announce itself. Iron can do the same. Sodium, magnesium, and calcium can also whisper their presence. The science then asks a practical question. How strong are the lines compared to the rest of the glow? Strength points toward abundance, toward grain size distribution, and toward the energy environment near the nucleus. One possibility is that a comet from another system is broadly similar to ours. The same messy mix of ice and dust, the same metals in trace amounts, the same physics of sunlight lifting layers into space. A competing view suggests that formation environments vary more than we expect, that some systems produce bodies with higher metal content in their outer parts, or with dust that liberates metals more efficiently when warmed. It remains uncertain whether early measurements for this visitor show anything outside the family picture. July spectra did not demand a rewrite. They set a floor for what is present and left open how those ratios may evolve with distance from the Sunday context stabilizes interpretation. When metals show in a coma, they rarely stand alone. Water fragments leave strong signals. Carbon-bearing molecules do as well. If nickel lines are unusually strong relative to those common features, then composition or grain processing deserves attention. Evidence is limited, but one inference is that a denser population of fine grains can boost certain TEPCA lines by presenting more surface area to radiation. Another inference is that the thermal history of the dust matters. Grains baked by past close passages can behave differently than grains newly exposed. For an interstellar object on a first known visit, past history is a blank. That blank invites careful humility. Mass and size play a role too. A small nucleus that is very active can flood the coma with fresh grains and gas, making metal lines easier to see without requiring a large bulk abundance. A larger nucleus with a calm surface can hide metals behind a thicker veil of conventional species. Without a resolved core and a tight size estimate, you cannot turn a spectral line into a density claim. The correct move is to pair spectra with time series photometry and with any future size constraints, then ask whether the whole picture fits a sensible model of mass loss and chemistry. A minority view holds that metals could hint at engineered material. The road to that claim is long and full of tests. A single line is not a passport. An engineered origin would require multiple signatures that resist natural explanation. Unusual isotopic ratios verified by independent teams. Light curves with geometric regularity that defy irregular tumble. Radio signals that drift in a way that matches the ephemeris and repeat under control observations. Without that stack, metal in a mist remains a natural story, and a beautiful one. There is another subtlety. Observation angle can bias what you see. Look through a thicker column of coma, and lines appear stronger. Look off to the side and you sample different grain populations. Instruments on Mars and on Earth will not share the same geometry. Comparing their spectra is not just about chemistry. It is also about lines of sight and calibration. This is why replication across platforms matters so much. Agreeing line strengths after proper correction carry weight. Disagreement asks for more work with lamps and flats before it asks for more dramatic ideas. The safest conclusion for now is restraint paired with curiosity. Metal lines do not move this object out of the realm of comet physics. They nudge questions about formation and dust. They remind us that small bodies are archives of their birthplaces, and that an interstellar fragment can bring a few grains of another star's story into our detectors. When more spectra arrive, we will read them against this steady background and see whether the ratios drift in ways that surprise. With composition anchored to what we can responsibly say, we can turn to the other half of the unknowns, size and mass. How heavy is a blur when the core hides inside a glow? What can brightness and distance really tell us about density before anyone resolves the body? That is the next puzzle, and it demands care with every assumption we make. Weight is the most tempting number in any cosmic mystery, yet it is the one most likely to mislead when all you can see is a glow. A comet's nucleus hides inside its own haze. Light you measure in a telescope is a mixture of sunlight reflected by dust, sunlight scattered by gas, and a small contribution from the solid body itself. To turn brightness into size, you must subtract the coma and then assume how reflective the surface is. To turn size into mass, you must assume a density. Each assumption widens the bracket. A small change in reflectivity can double or halve the inferred diameter. A similar change in density can swing the mass by an order of magnitude. Stack these uncertainties, and the honest answer becomes a range rather than a boast. Observers use a few tools to tame this problem. One is the radial profile, a simple plot of brightness as a function of distance from the center. If the glow follows a shape expected for a steady dust outflow, you can model and remove the coma's contribution near the core. Another tool is the phase function. the way brightness changes with the angle between sun, comet, and observer. Surfaces and dust clouds brighten differently as that angle changes. A series of measurements at different angles can isolate the fraction of light that likely comes from the solid. A third tool is the Afro proxy, a classic way to describe dust production with fewer assumptions. None of these methods measures mass directly. They constrain it by tying the coma to plausible production rates and by limiting how big the hidden core can be without contradicting the light you actually see. Albedo is the slippery word at the center of the puzzle. Dark surfaces reflect less light and look smaller than they are. Bright surfaces cheat in the other direction. Comet nuclei in our system tend to be very dark. If this visitor shares that trait, then a faint unresolved core could still be large. If it is darker or brighter than expected, the curve shifts again. This is why early mass talk should be gentle. You need either a direct size constraint or a very careful decomposition of the coma to claim anything beyond a range. Hubble's July images gave the decomposition a starting point, but left a wide bracket. Any mass estimate that pretends to be precise without closing that bracket is performance, not science. Spin complicates things further. A rotating irregular body can present more or less illuminated area to us across a period. If you happen to observe during a dimming phase, you will underestimate the size. If you observe at a bright phase, you will lean toward the upper end. Astronomers correct for this by collecting light curves and folding many nights together. That reduces the chance that a single exposure misleads. During the first week of October, the chance to extend the curve from Mars was valuable because it filled time when Earth-based data were thin. An improved period estimate helps everyone place their photometry on a fair baseline when calculating size. Density belongs to the last step of the chain. We know cometary densities in our system span a range from very light rubble piles to somewhat compact mixtures. An interstellar fragment could wander anywhere in that family and still be natural. Evidence is limited, but one inference is that a first-time visitor may carry more volatile material near its surface, which pushes densities lower rather than higher. A competing view suggests that only the tougher fragments survive long interstellar journeys, which could bias the sample toward denser pieces. It remains uncertain which trend dominates. Without a direct size and a measured non-grav push that implies mass loss rates, density arguments should remain provisional. You may have heard claims that the object is astonishingly massive or made of metal, because metal sounds like weight. Look for the algebra behind those claims. If the input size came from an upper bound, and the density came from a planetary core rather than a comet, the multiplication will impress, but it will not persuade. A responsible path ties mass to the faintest radius that still fits the light after coma removal, and to a density bracket that matches comet analogues unless spectra force a change. Anything outside that path must carry clear labels that it is speculation, and it must explain what independent observation could prove it wrong. There is one more way to triangulate. Non-gravitational terms in the orbit relate to how much gas and dust the nucleus throws off and for how long. If the orbit requires a stronger push than the measured brightness can supply, something is inconsistent. Perhaps the coma model undercounts fine grains. Perhaps the assumed size is wrong. By insisting that orbit fits and photometry agree, you push both mass and activity into a self-consistent box. That box might still be large, but it will be real. The right posture for now is patience with the blur. When more time series arrive, when post-conjunction spectra add chemistry, when Mars-based logs reveal how many hours were devoted to the stare, the bracket on, size will shrink. When the bracket shrinks, mass follows. Until then, the most accurate description is a range that respects what the images can and cannot tell us. Claims that jump the guardrail can be set aside politely and revisited only if future data insist. Every 3 parts, let us return to the through line. We are choosing careful bounds over attractive certainties. With the physics and the measurement caveats in hand, the story returns to people and process. A lawful pause can look like a blindfold, even when no one is hiding anything. To understand why that feeling lingers, we have to walk back through the rules that shape what can be said in public during a funding lapse, and how those rules can turn an ordinary delay into a legend. A funding lapse is not a drama, it is a procedure. The law that governs American agencies during those days is blunt. Do not spend what Congress has not provided. Managers translate that into lists, names, and tasks. Accepted operations continue to protect life and property. Everything else waits. The effect from outside looks like a curtain, but from inside it feels like traffic cones and detours. A press office that usually turns telemetry into plain language is told to stop. A web team that usually posts images is told to stop. A social media manager who would have threaded context through a tense week is told to stop. Flight controllers are told to keep spacecraft safe. The public hears nothing from 3 desks and a soft hum from one. The ear interprets absence as choice. In reality, the absence is compliance. Understand the chain that produces one public image in normal times. A scientist proposes or pre-approves a target. A planner turns that into an instrument sequence. A controller loads the commands. The spacecraft collects data. Raw packets land on secure storage. A pipeline calibrates those packets into science-grade products. A data archive ingests the products and exposes them to the world. A writer and a producer select a frame, add context, and push a post to channels. In a shutdown, the chain breaks near the end. The calibration can be delayed if the people who maintain the pipeline are furloughed. The ingest can be delayed if archive staff are furloughed. The post cannot happen at all because public communication is not accepted work. Break a chain in 2 places, and you get quiet even when the front half is running. This produces a second-order effect that is easy to miss. Scientists who would normally answer reporters, write quick notes, or clarify a rumor on a public forum become cautious, even when they are not furloughed. The rules on what counts as work are strict. A friendly clarification on a personal account can be interpreted as performing duties without authorization. Many choose to go dark rather than risk a violation. The tone of a community shifts from conversational to careful. Outside, observers hear that shift as evasive. Inside, it is self-protection. The international contrast amplifies perception. A European team that is not constrained by the American funding lapse continues speaking in the usual rhythm. They post an intent to observe. They post a reminder about constraints. They answer a few simple questions. That normalcy casts the American silence in high relief. People begin to speculate about motive. Motive is almost never the right variable to adjust. Capacity is. One group is allowed to speak. One group is not. The same machines in orbit keep circling regardless. There is a reasonable question that follows. Could someone hide an extraordinary finding inside this quiet? The accurate answer begins with permission. Classification is a separate process with its own authorities and paperwork. Nothing about a funding lapse automatically classifies science data. What the lapse does is slow the pipeline that would reveal ordinary results, and it mutes the people who would dismiss rumors quickly. If an anomaly existed, the same checks we have, already named, would still catch it when archives open. Timestamps, instrument modes, pointing, and orbit fits do not bend to narrative. A claim that survives those checks will not need a press office to be interesting. A second reasonable question asks whether this structure should change. The lesson of the first week of October is not that science hid a secret. It is that silence breeds story even when everyone is obeying the rules. Agencies can plan for that by pre-authorizing minimal, factual status lines that can be posted during a lapse by a tiny skeleton team. A single sentence saying instruments are safe and scheduled observations will be processed when operations resume is not a luxury. It is a pressure valve. The cost is small. The benefit is stability. Another improvement is to automate the publication of certain raw products with clear caveats. A nightly dump without interpretation can help third parties check times and modes, which in turn calms speculation without demanding staff hours that the rules forbid. Every 3 parts, let us repeat the through line. We are separating feelings created by timing from facts recorded by machines. When the quiet is procedural, the cure is documented receipts after the fact and a few steady signals during the pause. Both are possible within the law if they are designed ahead of time. Until such designs become standard, the public will keep encountering the same empty hallway during rare, high-interest events. That emptiness invites myth. Our way out is not to scold the myth makers, it is to publish the receipts and to teach people where to look for them. With that groundwork set, we can return to the core puzzle, whether any trace in the orbit or in the light suggests behavior that ordinary comet physics cannot explain. If the answer is yes, we will see it in the data. If the answer is no, the sky will have given us a quieter gift, a lesson in patience. The obvious watchers were not the only ones awake. Space is thick with sensors whose names rarely trend. Some belong to agencies that publish everything they can. Some belong to programs that publish almost nothing. If you want the full set of eyes that might have glanced at the visitor during the week of silence, you have to map a broader sky, then sort what could plausibly see from what is wishful thinking. The goal is not to feed mystery. The goal is to see how many independent threads might later tighten or relax the questions that October left behind. Begin with Europe, because their cadence remained normal. Mars Express and the Trace Gas Orbiter were the public anchors for the Martian Vantage. Elsewhere in the European fleet, there were cruise phase instruments with discretionary time. A spacecraft on a long arc toward the outer system can sometimes turn its camera outward and stare at a faint point for calibration and opportunity. If geometry favored a look in late October or November, those data could enrich the post-conjunction story even if they missed the Mars window. Such looks would not rival a dedicated observatory. They would add timing and color, which is often enough. Now look to China. Tianwen, one has orbited Mars since early in the decade. Its public communication is less frequent, but the hardware is capable of imaging and spectroscopy. It is reasonable to ask whether that team considered a pointing sequence during the same window. The answer is not known from public notes, and that uncertainty should be stated as uncertainty. If any products appear later, they will carry the same timestamps and modes that we have learned to trust. Until then, absence of a press item means nothing more than a different style of outreach. Commercial telescopes and survey networks form a second layer. Ground-based assets operated by universities and private consortia collect large volumes of sky every clear night. Many of them were hampered by glare in early October, yet their edges and twilight frames still matter. Automated pipelines flag moving points. When the object re-entered darker skies, these networks became the first to stretch the observational arc. Their data will flow into orbital solutions that do not care who paid the electric bill. Independent points act like ballast. They keep a narrative from tipping toward drama when the math is stable. There is also a class of sensors built for awareness rather than science. Space domain surveillance uses ground optics and radar to track satellites and debris. Most of those systems are tuned for near-Earth distances. Some can reach farther for special tasks but lose sensitivity rapidly with range. A visitor 30 million kilometers from Mars is a very hard radar target for anything built to defend orbital highways. Optical systems can do better in principle, yet they are scheduled to stare at catalogued objects with predictable paths. Retasking is possible. It is also rare when the return is faint science rather than mission protection. A minority view holds that such sensors might have collected unusual data and kept it classified. That view is difficult to test. The honest response is to evaluate public data for consistency first. If public curves fit, a hidden cache of extraordinary measurements is not required to explain the event. Amateur observers belong in this inventory as more than a courtesy. Skilled amateurs with mid-sized telescopes and careful methods supply photometry and astrometry that archive swiftly and that others can check. Their work is invaluable on the shoulders of the glare period. It pins down brightness trends before and after the dead zone. Amateur forums also act as early warning for claims. If someone sees a sudden jump in magnitude, others can attempt replication the same night. Agreement across continents is a stronger anchor than a single dramatic post. Radio listeners add a different flavor. Most comets do not sing at narrow frequencies that a backyard dish can hear. Still, a few groups record dynamic spectra during interesting passes, if only to rule out foolish hopes. A clean null result with good controls is a gift to a community trying to stay honest. It shows that an attractive avenue was covered and that nothing stood above noise. If any radio team claims a line that drifts in step with the ephemeris, the bar for replication is clear and high. Multiple stations. Shared raw data, precise timing. Until those pieces appear, radio talk belongs in the bin labeled curiosity, not claim. There is a final quiet watcher that people forget, the archive itself. Space missions store more than they analyze in the moment. Calibration frames capture backgrounds, star tracker cameras record fields for guidance, engineering sensors write housekeeping at fine cadence. Later, when interest rises, teams can search those side channels for serendipitous traces. A faint streak crossing a calibration frame can be aligned with an ephemeris and retroactively become a point on the orbit. A small color sample in a context camera can add to a spectrum. Recovery work like this is patient and unglamorous. It is also a way that science rescues value from periods when the main instruments were not aimed on purpose. What matters about this census is not the thrill of secret eyes, it is the redundancy that reality prefers. If the visitor behaved like a comet, that behavior will echo through many small records. If something unusual occurred, the same redundancy makes invention harder. Claims will collide with independent streams and either survive or crack. That is why a wide map of watchers is reassuring. It means no single point of failure controls the story. Next, we will test that reassurance against a fresh risk. A quiet week spawned loud claims of missing frames, altered files, and unscheduled maneuvers. Some of those claims are recycled myths that appear whenever a feed freezes. Some are sincere misreads of normal pipeline behavior. A few deserve a checklist. We will take them one by one and show how simple receipts can separate an error from an event. Begin with the loudest rumor, the one that repeats because it feels cinematic. Frames were posted, then pulled, then replaced with something different. It sounds like a plot beat. The prosaic truth is that archives breathe. Pipelines ingest products, assign temporary identifiers, run calibrations, attach headers, and sometimes roll back a batch when a calibration file is found to be out of date. To tell the difference between a cinematic pull and a routine correction, you read the receipts that live in file systems. Version tags should change. Processing notes should list the software build. Checksums should differ in a way that matches a reprocess, not a hand edit. If a record shows removal with no replacement and no note, that deserves a question. Most of the time, the tree shows a clear lineage, from raw packet to calibrated image to reissued product with a new time. That lineage is boring, and boredom is a friend. Next, the claim that entire blocks of time vanished. Here, the fix begins with a calendar, a geometry table, and the ground station schedule. If a spacecraft did not have a downlink pass within a given hour, no file can exist for that hour. If a track was lost to weather or to a higher priority asset, the gap is normal. If the spacecraft was in eclipse or in a thermal configuration that forbade the instrument to open, the gap is normal. Logs record these states. When a real hole appears, it stands out because passes existed, configuration was nominal, and the instrument timeline shows a planned observation that never reached the archive. That is rare. When it does occur, it usually ends with a dull story about a corrupted file header or a mispoint that missed the target and produced a frame that the automated system rejected as empty. Anomalies of that type can be recovered, and the recovery leaves a paper trail. Unscheduled maneuvers are the rumor that wears confidence like a badge. The assertion is that thrusters fired and the public was not told. Spacecraft do maneuver, often for reasons as humble as momentum management or antenna geometry. Those events are not invisible. Radio tracking measures, Doppler and range. A burn changes those curves in ways that analysts for navigation see at once. Post-event ephemerides carry the new state. The question is not whether a burn happened. It is whether a burn lined up with a supposed attempt to point at a faint target or to avoid pointing at one. The timeline answers that. Housekeeping carries thruster valve states and reaction wheel speeds. A navigation update carries a fit note. If a burn and a claimed observation align in a suspicious way, you can say so with specifics. If not, the rumor returns to smoke. Metadata redaction is another familiar story. Someone opens a flexible image transport file and finds a blank field where a target name should be. This is usually a matter of template headers or privacy for personnel, not science. The crucial fields for scientific work are times, instrument states, pointing, and calibration references. If those are intact, the absence of a human name or a provisional target string means nothing. If the crucial fields are missing, the file is incomplete and should be flagged as such. Archives often carry caution labels for these cases. The label is the opposite of a cover. It is an admission that a product should not be used for analysis until a repair is made. Then there is the claim of brightness jumps that no one else sees. Here the method is to replicate and to fold in known nuisances. Atmospheric extinction varies with altitude above the horizon. Twilight gradients bias, 0 points. Small apertures collect different fractions of coma light as seeing changes. A careful photometrist corrects for all of these, then publishes both the number and the method. When another observer at a different site repeats the measurement within an error bar that makes sense, the event gains weight. When replication fails across nights and instruments, the first report joins the long shelf of noble tries. Neither outcome is scandal. Both outcomes are how truth emerges. A more subtle rumor claims that tracking elements shifted in a way that implies a nudge. The correct test is to pull the minor planet center updates and plot residuals before and after the week in question. If a shift is real, it will change the way new data fit for many observers, not just one. Analysts add simple, non-gravitational terms when data demand them. If the demand appears suddenly and only in one subset, the cause is likely a calibration issue or a cluster of low-altitude observations that bias one direction. If the demand grows gently across weeks, that is nature, not intrigue. All of these checks benefit from one habit that rumor avoids. Write down your disproof before you seek your proof. If you claim frames were pulled, you must accept that versioned reprocessing with clear notes satisfies the concern. If you claim an unscheduled maneuver, you must accept that navigation fits without a burn close that door. If you claim a brightness jump, you must accept that independent null results with stronger controls deflate the claim. This posture does not kill curiosity. It makes it honest. Every 3 parts, let us restate the through line. We are trading drama for documentation so that whatever tension remains is earned. With the checklists in place, we can return to the part of the story that invites suspense without invention. If something truly interesting happened in early October, subtle signs will appear first in the orbit and in the light. The richest place to look for those signs is in the long curve of brightness that spans before, during, and after the dead zone. That curve is the heartbeat of the visitor. It tells us if the pulse quickened when Mars had the better view, and whether the beat changed as the object rounded the Sunday. A comet's brightness curve is the simplest diary it keeps. Each point on the graph is one night, one instrument, one measure of how much sunlight, dust, and gas return to the observer. String the points together, and the line becomes a heartbeat. It speeds up as the object draws closer to warmth. It slows as the object recedes into cold. Small flutters mark rotation. Sudden spikes mark outbursts. Long plateaus mark periods of steady flow. To understand the week that everyone argued about, you place that week in the middle of a wider record and you look for changes that survive the noise. Comparison is everything. Before the dead zone, the curve that July and August produced set the baseline. After the dead zone, November and December promise the check that either confirms a calm pulse or reveals a strain. Before the pause, the early light was faint and steady. Measurements scattered within healthy error bars. A few teams reported gentle brightening that matched distance and phase angle. The curve looked like a textbook ramp toward perihelion. There were hints of rotation if you squinted, small rises that repeated every few hours on good nights. Those hints did not synchronize cleanly across sites, which is normal when geometry and weather vary. The important fact was not the small wiggles, it was the lack of drama. Nothing leaped off the page. This was a working comet seen at long range. It breathed quietly. During the dead zone, Earth-based eyes were half shut. Mars-based eyes, if tasked, could have watched the same heartbeat with better contrast. The question everyone wants the curve to answer is blunt. Did the pulse quicken in a way that cannot be explained by ordinary activity or by a brush with space weather? The honest way to pose that question is to look for a step or a hump centered on the week in question. A step would mean brightness rose to a new level and stayed there, as if a fresh patch of ice had opened permanently. A hump would mean a temporary surge that relaxed, as if a small collapse exposed volatiles then exhausted them. Either shape would be interesting. Neither would immediately imply anything unnatural. Both would have to be reconciled with orbit fits and with any plasma records from the same days. After the dead zone, the sky returns as a partner. Late November brings a clean horizon and cooler air. December brings long nights and many chances to stack exposures. If the pulse shows no step and no hump, then the week of silence likely contained nothing dramatic. If the pulse does show a shape, then the shape must be cross-checked. Teams in both hemispheres should see the same pattern once you account for viewing angle. The phase function can be applied to level the numbers. The scatter will narrow when many points are folded. If only one region or one class of instrument reports the rise, calibration is the first suspect. When multiple lines agree, you can begin to assign causes. Rotation sits on top of this long trend, like a thinner rhythm. A well-sampled curve allows observers to fold data over candidate periods and watch for alignment of peaks and troughs. A clean match marks a probable spin. A messy match marks either complicated rotation or blended systematics. The value of Mars-based sequences in the week of interest would be greatest here. A long stare from a stable platform can capture several cycles without the interruptions that ground-based nights suffer. Place that sequence beside pre- and post-data, and the rotation solution sharpens. With a period in hand, you can ask whether any change in brightness during the week came at a particular spin phase. If it did, a jet tied to a surface feature becomes the simple explanation. Color adds another small but useful layer. When instruments measure brightness in 2 or 3 bands, changes in color index can signal shifts in dust size or gas dominance. An outburst rich in fine grains often produces a bluer coma for a short time. A. The dominance of large grains moves color the other way. When a reported brightening coincides with a color shift that matches known comet behavior, you gain confidence in a natural cause. When color does not budge while total light jumps, you double-check methods before you reach for exotic stories. The same logic holds for polarization if anyone measured it. Changes in how light is polarized can betray particle properties in the coma. These are not decorations, they are discriminators. Space weather must be plotted on the same time axis. The solar wind rarely rests for long. Coronal mass ejections sweep through the inner system. Shocks and density waves change ionization and tail structure. If a solar event encountered the object near the Mars window, then a hump in brightness that relaxes quickly has a ready-made cause. Instruments at Earth and satellites between Earth and the Sun record these events and post them in public timelines. Later, when mission archives open, those timelines can be matched to any oddity seen from Mars. Agreement does not prove causality, but it sets the stage for a persuasive case. The elegance of the heartbeat method is that it turns many small efforts into one judgment. No single telescope needs to carry the story. Each point pulls the curve in a direction, and the curve settles where the truth is strongest. If the visitor kept breathing like any other comet, that truth will look pleasantly boring. If the visitor's pulse did something unexpected, the shape will guide us toward cause without theatrics. In either outcome, the line will make better television than a rumor, once you know how to read it. There is a moment in every comet story when the curtain drops on Earth. The object rounds the Sun, slides into conjunction, and vanishes inside daylight. Observers put down coffees and wait. Waiting is not empty, it is preparation. Perihelion concentrates energy. Sunlight climbs to its peak for this passage. Surfaces crack, pores open. Old frost becomes gas. Some comets answer with a slow rise and a slow fade. Others answer with fireworks. We cannot watch the peak from the ground when the sun sits between, but we can script the return. The second chance begins the instant. The object steps out of glare and back into the dark frame of morning or evening. If October was the week of suspicion, December is the month of receipts. The playbook is simple. First, pin down where to look and how bright to expect. Ephemerides from the orbit solution set, sky positions to arc minutes. The distance from Earth and the phase angle yield a magnitude forecast with fat uncertainty bars. That forecast tells mid-sized observatories they can try broadband photometry. It tells large facilities whether to plan spectra in their fainter modes. It tells amateurs which cameras and exposure lengths might be worth a run. Then, stack nights. One night is a data point. A week is a curve with personality. 2 weeks is a story with cause and effect. The most valuable early sequence after conjunction is a run of long stares. Choose a site with stable weather if possible. Keep the cadence steady across several hours to chase rotation. Repeat within a few days to test whether the same shape repeats with the same period. If the spin solution holds, fold all data on that period and tease out small changes that would otherwise hide in scatter. A rise in average brightness across nights means activity is still ramping, or that a fresh patch opened near perihelion. A rise that comes and goes in a single rotation phase points to a jet tied to topography. These are natural paths to explanation. They do not forbid surprise, they discipline it. Color and spectra are the second priority. If resources are scarce, choose 2 bands that straddle the region where dust color changes are most telling. Record a color index every time you measure total light. If an outburst occurred near perihelion, fine grains should still be drifting away in the first weeks after. Fine grains often make the coma bluer for a short time. A return to redder tones as grains disperse is a signature that many comets share. Spectra extend this logic. Even modest resolution can track the strength of water-related bands and simple carbon species. A rising gas lines that lags a dust brightening by days is a clue about how deep the warming reached. No single line will carry the argument. The pattern across lines will. The third priority is comparison. Northern and southern sites should exchange notes. A body that is outgassing will not present the same coma to all angles. Phase corrections and geometry shifts need to be applied. Once corrected, curves from different hemispheres should agree within errors. If they do not, calibration is the first suspect. This is the moment when teams share reduction scripts and reference stars. It is also when amateurs with rigorous methods become essential. Their timestamps and transparent processing give professionals a way to cross-validate without waiting for slow institutional pipelines. Many hands pull the curve toward truth. A watch should be set on the orbit at the same time. Fresh astrometry with good star catalogues can tighten the fit radically once the object returns to a comfortable elongation. If the post-conjunction points fall where the pre-conjunction model predicted, the path is calm. If they fall off the line by more than the brackets allow, then the model must accept non-gravitational terms or admit that an event near perihelion changed things. The beauty of this test is its indifference to story. It does not care what anyone hoped to find. It cares whether the math meets the sky. Space weather remains an invisible partner. Offices that monitor the sun publish lists of eruptions and arrival estimates for shocks in the solar wind. Overlay those times on the post-conjunction brightness curve. If a bump appears 2 days after a predicted arrival, that is not proof of cause, yet it is an invitation to test the idea with more detail. Pull particle data from spacecraft that sit between Earth and the Sunday. Look for changes in ion tail structure in wide-field images. If the signs agree, the case for a weather-driven surge grows. This is the healthy loop between environment and response that turns coincidence into correlation and sometimes into causation. There is a narrative temptation to call the reappearance a verdict. That is not quite right. It is more like a second deposition. You ask the same questions in kinder conditions and see whether the answers change. If the comet looks ordinary in December, then the legends spun in October collapse on their own. If the comet looks lively, then the liveliness will have dates and numbers that everyone can see. Either outcome is a win for the audience and for the field, because clarity is entertainment when the subject is the sky. Every 3 parts, let us restate the through line. We are letting the calendar and the curve do the work that rumor tried to do overnight. When the second chance plays out, we will have what matters most. A continuous record that spans before, during, and after the quiet. With that record in hand, we can translate observations into a ranked set of explanations, from mundane first to exotic if and only if necessity demands. That ranking is not just a style choice. It is a compass that keeps a curious mind from walking in circles. When data begin to flow, you need a scoreboard that resists mood. The cleanest way is to line up competing explanations and ask what each one predicts that the others do not. Then you test those predictions with receipts. Start with the quietest story. Bureaucratic coincidence says the silence was a policy echo, not a scientific signal. It predicts that European logs will show attempts during the Mars window, that American logs will fill in later with routine modes and a few targeted stares, that image and spectrum products will arrive in batches after operations resume, and that the brightness curve will follow distance and phase without a permanent step. If this story wins, timestamps align with opportunity. Residuals in the orbit shrink as points are added, and color and spectra look like a family portrait of a comet. The second story keeps things natural but noisier. A space weather nudge proposes that solar wind changes near early October boosted activity briefly. It predicts a hump in brightness centered within a day or two of an arriving shock, a mild enhancement in ion-sensitive features, perhaps a short-lived blue shift in color index that relaxes. It also predicts that orbit fits need only small non-gravitational terms, not step changes. If this story wins, MAVEN or near-Sun monitors record a disturbance, and Mars-based or Earth-based sequences show a bump that fades within days, not weeks. The third story sharpens the natural case. A jet awakening suggests that a new active region turned on, the sunlight angle shifted near the Mars window. It predicts a modest step upward in average brightness that persists, a periodic modulation tied to rotation that becomes clearer as time series accumulate, and small but coherent changes in color at a particular spin phase. It also predicts orbit fits that prefer steady, non-gravitational terms aligned mostly with the Sun to comet line. If this story wins, folding the light curve on a single period reveals a repeatable crest and trough, and spectra show ordinary gases with no strange ratios. The fourth story is the heavy one, the idea of a dense or metal-rich nucleus. It remains speculative because mass is the hardest number to nail. It predicts slower than expected response to solar heating for a given size, weaker non-gravitational terms than a high-activity light curve would imply, and persistent spectral quirks across independent instruments, not a single line in a single setup. It also predicts that mass loss rates inferred from brightness will look small, for any size estimate on the upper end, otherwise the energy budget breaks. If this story wins, it will be because multiple teams converge on size at the high end, with very low albedo and low acceleration, not because one plot went viral. The fifth story says there is nothing to see except paperwork and delay. A black budget capture of data claims that classified sensors watched and filed their work elsewhere. This story is difficult to test directly. It predicts little in public beyond a normal curve and a normal orbit. It also predicts occasional rumors from unnamed sources that never cohere. The honest way to weigh this story is to see whether public data makes sense on their own. If they do, then hidden data may exist, but they are not needed. If they do not, then either hidden data might clarify, or the public record contains errors that will be corrected. This story does not change the comet. It only adds a shadow that cannot be measured. The sixth story is the loudest, and therefore must carry the heaviest burden. An engineered or guided object would not move like sunlight and vapor alone. It predicts velocity changes that do not correlate with activity, spectra that resist natural chemistry across multiple platforms, geometric light curves with crisp regularity that survive independent analyses, narrowband radio, or optical signals that drift exactly as the ephemeris requires and that repeat on command, and perhaps thermal behavior that violates simple models. If this story wins, it will be because evidence piles into a tower that natural explanations cannot match, not because imagination led the parade. A ranked board like this is not a bet slip, it is a discipline. It tells you to accept the quiet story unless data force you to climb the ladder. It also tells you what would make you climb. A permanent step in brightness without a plausible jet phase, you climb one rung. A hump that tracks a solar shock and fades, you stay. Residuals that twist despite. Honest, non-gravitational terms, you climb and check everything again. A stack of independent spectra that show ratios out of family, you climb with care. A signal detected by multiple stations with shared raw files and consistent drift, you climb quickly and alert the world. Every 3 parts, let us state the through line again. We are choosing the explanation that fits the most receipts with the fewest contortions. The magic of this ranking is that it is public and simple. Anyone can follow along. When a new plot arrives, you ask which prediction it matches. When a rumor appears, you ask which rung it tries to skip. The ladder does not forbid wonder. It protects wonder from collapse by making it earn its height. With that frame in place, we can shift from judging explanations to planning actions. The second chance after conjunction is not just for professionals. A crowd of careful eyes can shorten the distance between claim and test. The next part is a practical field guide for joining that effort without stepping on each other's cables. A mystery is best solved by many careful hands, provided those hands move in rhythm. After conjunction, the window opens for everyone with a modest telescope, a patient computer, or just an eye for good record keeping. The goal is not to flood the world with pictures. The goal is to produce measurements that fit together. Think of it as building one long exposure out of thousands of short ones. Each person holds one small frame. If each frame carries honest timing, clear methods, and a place in an open notebook, the final image will be sharp. Begin with time. Every observation must carry an accurate timestamp in coordinated universal time. Computer clocks drift. Check yours against a trusted time source before every session. Record the start and end of each exposure. If you stack frames, retain the individual times in a table. The heartbeat curves that reveal rotation and outbursts rely on minutes. A drift of even a small fraction of a minute can smear a pattern and turn signal into noise. When many observers agree on timing, their curves fold into a single rhythm. When timing slips, the song goes out of tune. Next, choose what you will measure and declare it in advance. Photometry is a promise to measure brightness. That promise includes your filters, your aperture size on the image, your calibration stars, and your method for removing sky background. Write those choices down in a header at the top of your notebook for the night. If you change a choice, say so and say why. If you do not have standard filters, you can still report relative brightness in a single band, provided you keep your setup fixed and you state your detector and optics clearly. Consistency is a gift to anyone who will fold your points into a combined curve. Astrometry is a promise to measure position. That promise includes your star catalog, your plate scale, and your distortion solution. Use the best catalog you can access. Solve your field carefully. Report uncertainties. A good astrometric point that carries a real uncertainty helps the orbit fit more than a point that pretends to be perfect. If clouds or wind degrade your frames, do not be brave. Save the camera and try again on the next clear night. The orbit cares about clarity more than volume. If you prefer to listen rather than look, radio experiments can help by ruling out eager fantasies. A small team using software-defined radios can record dynamic spectra when the object is high and when it is near the horizon for control. Always collect off-target controls. Record in a format others can open. Share raw files as well as processed plots. If anyone claims a narrow signal that drifts with the ephemeris, others must be able to test the same time slice and either confirm or refute with the same tools. A clean null across stations is not an absence of value. It is a fence that keeps weak claims out of the yard. Open notebooks are where this work becomes a communal instrument. Host your logs and data in a public repository that preserves version history. Each entry should include date, start and end times in coordinated universal time, location, equipment, settings, and weather. Include a small paragraph on conditions and any surprises. If you reprocess a dataset, do not erase the old one. Add a new version and explain what changed. A chain of versions that tells a story from raw to refined is the opposite of secrecy. It is teachable honesty. Coordination prevents duplication without stifling independence. Regional groups can agree on nights and targets. One group can chase long sequences for rotation. Another can gather color indices with shorter runs. A third can focus on early evening arcs that bridge to late-night arcs at a different longitude. Amateurs can ping professionals to ask for cross-checks on reference stars or for advice on handling a faint gradient. Professionals can point to public tools and reference fields. The exchange should feel like a friendly shop counter. No one owns the sky. Everyone benefits when methods are transparent. Quality control is a shared practice. Before posting a claim of a brightening or a dip, test your pipeline with a nearby field. If the trend appears there too, you have a calibration issue. If the trend persists only on frames near the horizon, you have an extinction issue. If the trend vanishes when you change aperture size, you have a coma fraction issue. Write what you learned so the next person can skip the mistake. When in doubt, attach your raw frames and let others try their own reduction. Shared raw is a peace offering that often diffuses argument before it hardens. At regular intervals, pull the community results into a living curve. Plot brightness against time with colors for instruments and symbols for bands. Mark known solar events on the same axis. Post the plot with a short reading that separates what is measured from what is guessed. Invite others to add their points by opening a simple issue with their files and methods attached. This small ritual turns many voices into one record. That record is the public face of the project, and it is a better antidote to rumor than any thread of opinion. Every 3 parts, let us rest the through line in front of us. We are building receipts that anyone can check, and then following those receipts wherever they lead. When the second chance window closes, the crowd will have built something that did not exist in early October. A timeline that spans the silence with facts. That timeline will not just solve this one story, it will become a template that people can reach for the next time an interstellar object crosses a political storm. The best reply to a quiet week is a louder archive. The best reply to a rumor is a shared plot that refuses to bend. Picture 2 travelers sharing a lane of space for a brief hour. One a planet wrapped in a thin cloak of air and relic magnetism, the other a cold visitor dragging a veil of gas and dust behind it. 30 million kilometers sounds large to our senses, yet in orbital terms it is a near pass that invites small effects. The first question is gravity. Mars has mass enough to bend paths gently well beyond the moons that circle close. A flyby at this distance imparts a minute deflection, not a cinematic sling, more a fingertip on a spinning coin. You can calculate the scale with simple numbers. The tug falls with distance squared, and the time under influence is only a few days for a fast mover on a hyperbolic path. The result is a drift that precision astrometry can detect if measurements bracket the pass. The pass does not capture. The pass cannot capture at that range. It can paint a tiny smear on the shape of the hyperbola that orbit fitters later peel away with satisfaction. Tides are the next worry to test. Tidal forces raise bulges when gradients in gravity stretch one side more than the other. At planetary distances, those gradients are negligible for a small nucleus. There is no plausible stretch that could tear a body apart at 30 million kilometers from Mars. A nucleus might already be a loose assemblage of rubble. If so, its own spin and outgassing are the dominant sculptors. The planet's pull is a spectator. The right place to look for change is not in catastrophic breakup. It is in the delicate accounting that orbit residuals and light curves provide. If a tidal assist mattered, it would appear as a barely different trajectory and a slightly altered rotation state over very long baselines. The measurements we have and the measurements we expect were designed for that level of subtlety. They also tell us when we are chasing ghosts. The space around Mars has character. The planet lacks a global magnetic field, yet it carries patches of fossil magnetism in its crust, and it stands in the blast of the solar wind. That combination builds a bow shock and a long wake of charged particles and fields. Instruments like those on MAVEN have drawn this structure for years. Could a comet 30 million kilometers away interact with that space weather in a way that matters? The honest answer is that direct interaction at that separation is unlikely to add energy or momentum in a measurable way. The plasma environment of Mars extends far, but not that far, with enough density to push a distant coma. The more realistic pathway for influence runs the other direction. A solar disturbance that shakes the Martian environment can shake a comet tail across a wide volume. If a coronal mass ejection passed through the region around the time of the near pass, both the planet and the visitor could respond, each in their own way. Mars would show changes in ion escape and local fields. The comet would show tail kinks and brief brightness changes. Correlation would be interesting. Causation would still be solar. Photons do what gravity and plasma cannot at that range. Sunlight is the main actor for the visitor. Heating sets the rate of gas escape. Radiation pressure pushes dust into graceful arcs. The presence of Mars does not change the sunlight the comet feels, except through the small geometry of distance to the sunday. That geometry was already in the orbit. If the brightness changed during the period of closest approach, the clean tests will point first to internal processes and external solar weather, rather than to planetary proximity. A new jet could wake as surface facets met a better angle. A shock could seed ions and temporarily boost emission lines. In both cases, the timing might overlap with the Mars pass without being caused by it. There is one more path where Mars could help in quiet ways. Vantage matters. Cameras in orbit around the planet looked at the visitor from a different line of sight than observers on Earth. That difference changes phase angle, the angle between sun, target, and camera. Changes in phase angle alter how dust brightness scales with distance from the center. They also change how tail structure projects onto the sky. A series of frames from Mars during the window, even if coarse, could capture a light curve segment at a phase that Earth could not access, then hand that segment to teams on Earth as a missing bar in a musical score. Later, when Earth regained a clean elongation, the two vantage points would bind together as one continuous composition. Skeptics sometimes ask whether a covert spacecraft could have used the Mars pass as cover to approach the visitor. The physics answer is practical. Rendezvous with a fast interstellar object requires deep reserves of delta V and exquisite timing. Using a planet as a base does not remove that cost. The distances remain harsh, the window remains tight. The instruments that could confirm such a stunt would be the same instruments we already use to fit orbits and record light. They would tell us if a nudge occurred. They would tell us if a track suddenly curved on a timescale that no plausible outgassing could explain. Absent those signatures, the story of approach remains entertaining and unnecessary. The correct attitude toward the Mars proximity is respect for small influences and excitement for geometry. The pass gave orbit analysts a chance to measure a subtle gravitational brush. It gave plasma physicists a shared clock if the sun sent a shock through the region. It gave imagers on Mars a different angle, and thus a different kind of truth. None of these are headline fireworks. All of them are the kind of details that, when woven together, turn a week of speculation into a page of science. When those pages arrive, the proximity will look less like a stage for intrigue and more like a fortunate alignment in a patient investigation. Sometimes, the most useful clue is not new at all. It sits in a hard drive that has been online for years, waiting for someone to ask a different question. Astronomers call these finds precoveries, earlier images where a target appears before its official discovery. For an interstellar visitor, a precovery tightens everything. It adds weeks or months to the orbital arc. It shrinks uncertainties. It can even reveal whether the object was already active far from the sun or woke only recently. Old frames do not care about shutdowns. They are immune to October moods. They only care about whether you look in the right place with the right search pattern. The method is straightforward and patient. Start with the best current orbit and integrate it backward to dates covered by wide field surveys. Compute a sky path with uncertainty, regions that swell as you go back in time. Then query archives, not just glamorous telescopes but the quiet workhorses that image the same fields night after night. Panoramic surveys, twilight surveys, calibration cameras that map star flats. Even star tracker frames on deep space missions can help if their fields and times line up. You do not need a pretty comet to win. You need a moving point that shifts between consecutive exposures in a way that matches the predicted rate. Stack those exposures along the predicted motion, and the point climbs out of noise like a shy animal. Each precovery that survives vetting pays twice. It adds a position and a time to the orbital fit, which forces the model to respect a longer history. It also sets a floor on brightness at a larger distance. If the object was visible in a modest exposure months earlier, then activity was already underway. If nothing is found above a firm limit, that too is information. It tells you that the coma was faint or that the nucleus alone could not be seen at that phase. Either outcome sharpens the narrative about when and how the visitor woke. Old frames answer in quiet, declarative sentences, while the present argues in excited questions. Precoveries are not only for ground-based surveys. Space observatories point with discipline and record with care. Hubble archives, for example, are rich in fields taken for unrelated science. If the path of the visitor crossed a field that was imaged for a galaxy cluster or a calibration run, the frames might carry a tiny streak near the edge. Those artifacts often went unnoticed because the original teams did not care about moving specks. Now the speck is the star. Cross-matching coordinates and times against these stars can turn an afterthought into a precious dot with a perfect timestamp and exquisitely known pointing. Mars missions have their own hidden troves. Not every image is a grand panorama or a surface mosaic. Instruments take sky frames for calibration, for flat fields, and for pointing checks. Those sky frames sometimes include stars. If the timing and the boresight align with the predicted ephemeris of the visitor during early October, one of those frames could add a faint detection from the vantage we cared about most. Even a non-detection with a strong upper limit matters. It says the object remained below a certain brightness then, which can rule out dramatic outbursts that rumors claimed. There is another archive that sounds humble and is anything but. Amateur repositories. Experienced observers upload nights of images to community servers. The quality varies. The best are carefully calibrated with bias, dark, and flat frames, and they carry precise times. The density of coverage is often better than the professional network because weather patterns are varied and motivation is high. Search scripts that scan these stacks for moving points along. Predicted tracks can flag candidates in minutes. Human eyes then confirm the gentle shift across a night. A grassroots precovery feels small at the telescope and large when it lands in the orbit fitter's inbox. The discipline here mirrors what we have practiced throughout. You declare how you searched. You record which archives you queried. You state your thresholds. If you found nothing, you post the limits so others do not duplicate labor. If you found a candidate, you share the cutouts and the registration stars. Another team should be able to follow your path and land on the same pixel. If they cannot, you do not have a precovery. You have a rehearsal. That honesty is not just etiquette. It keeps the common record clean, so that when a true precovery appears, It strengthens the whole scaffold. Recoveries also help with the most stubborn quantities, reflectivity and mass loss. If a detection far from the Sun shows a measurable coma, you can infer that some volatile species were active at large distances, that favors certain compositions over others. If multiple precoveries and postcoveries show a steady rise consistent with standard behavior, you can treat any short-term spike near the Mars window with more caution. It becomes a wrinkle rather than a reinvention. Old frames dilute the power of a single week to dominate the story. Every 3 parts let us rest the through line. We are building the longest possible timeline so that one noisy chapter cannot claim the whole book. When the precovery hunt is done, the orbit will be tighter, the brightness history longer, and the space for speculation smaller. That is a good trade. It does not kill suspense. It aims suspense at the right remaining mysteries. If anything truly odd survives this longer view, it will be harder to deny and easier to prove. If nothing odd survives, then we have learned again that patience plus archives beat adrenaline every time. From this vantage, we can touch one last speculative thread that audiences love and that science keeps at arm's length. Did anyone hear a deliberate call? What would a real signal look like, and how would we know we were not fooling ourselves? The most electric word in a story like this is signal. People imagine a beacon, a tone that climbs and falls in perfect sympathy with the comet's motion, a whisper that turns into proof on a laptop screen. The path from imagination to evidence is long, careful, and full of ways to fool yourself. Start with the medium. A deliberate call would most likely ride radio or optical light because those bands travel cleanly across cosmic distances and can be detected with instruments we already operate. Nature also fills those bands with noise. Lightning on Earth, satellites in orbit, air traffic, power lines, and ignitions produce radio clutter. Stars flare and glow. Lasers on the ground and in orbit add brief spikes to optical sensors. Sorting this environment into human and natural takes method, not hope. A real search begins with the ephemeris. The object's position and velocity, relative to the receiver, determine the way any narrow tone would drift in frequency across time. That drift is not optional. Motion stretches and compresses waves. It is a fingerprint. A candidate's signal must show a drift rate and direction that match the predicted motion during the observation window, and it must do so after you remove the drifts that the receiver hardware and atmosphere impose. If the tone does not move as the ephemeris demands, it is interference. If it does move correctly for a few minutes, the next test is whether the tone disappears when you move the telescope off target and reappears when you return. This simple on-off cycling is the heartbeat of verification. Replication is the next gate, and it is tall. One facility can be fooled by a local transmitter that sneaks through filters, or by a satellite that happens to pass across the beam. 2 facilities on different continents using different front ends are rarely fooled in the same way at the same time. A candidate that appears at one site should be scheduled for immediate follow-up at another site with the same center frequency and bandwidth, and with synchronized clocks. Both teams must record raw dynamic spectra with GPS-level timestamps. Both must archive the control pointings as well as the on-target scans. A signal that repeats at the same sky location and shows the same drift pattern under these conditions becomes worthy of cautious excitement. The discipline does not end there. Content testing is slow but essential. A deliberate beacon might be a pure tone that serves only to announce presence. It might also carry modulation that could encode information. Searching for structure in a faint tone requires high signal-to-noise, which often means longer integration or a larger dish. During that time, you keep testing the basics. Does the signal vanish when the object sets? Does it appear at the right Doppler offset when the object rises again? Does the drift rate evolve exactly as the changing geometry predicts? If the answers stay yes for days and weeks, the claim grows roots. If any answer turns no, the claim returns to the compost heap where most candidates end. Optical searches carry their own hazards. A narrowband laser flash would be an obvious sign, but meteors, glints from satellites, and instrumental ghosts can mimic flashes. The response is the same as in radio. Use on-target and off-target cycles. Use multiple instruments. Demand repeated detections that track the predicted motion. Store raw frames and timing solutions so that other teams can test your reduction. A pile of single-frame thrills does not add up to a case. A small number of repeatable events that march with the ephemeris across nights begins to do so. It remains uncertain whether any listening during the early October window met these standards. The geometry was poor for most ground-based radio facilities. The Mars Vantage offers a romantic idea that an orbiter might have heard something. Orbiter radios are not designed for this task. They lock to deep space network carriers and downlink telemetry. They are poor spectrum survey instruments. Even if an orbiter heard a tone, it would need to prove that the tone drifted as expected against its own motion, which is a deep challenge for a platform that is not built for discovery in crowded spectrum. The most credible arena for a claim will therefore be the period after conjunction, when Earth-based dishes can stare for hours under clean skies with clean controls. One possibility is that a team will report an intriguing candidate during that second chance. The right response from the community is immediate openness. Post the time ranges. Post the frequencies. Post the drift model used. Post the raw. Invite others to check with the same parameters. If the candidate survives this storm of attention, it will either blossom or fade on the merits. A competing view suggests that any true beacon would be glaringly obvious, and we would not still be debating method. Reality is often less theatrical. Signals ride pain thresholds near the noise. We owe them rigor and calm. Every 3 parts, let us rest the through line. We keep wonder alive by asking it to pass tests that are simple to state and hard to fake. If no signal appears, the sky does not become less interesting. We will have set limits that future stories can cite, and we will have exercised a muscle that atrophies without practice. If a signal does appear and survives, the rest of this documentary changes tone in an instant. Until that day, the sound we listen for is the click of clean methods linking together across distance, a chorus of careful no, and maybe that keeps truth within reach. Soon, the inboxes will fill. Archives will post batches with neat timestamps. Press rooms will warm up. Comment sections will stir. Decision time does not look like a gavel. It looks like a desk with 4 windows open. Orbit fits in one. Light curves in another. Spectra in a third. Housekeeping logs in the fourth. The trick is not to let the first dramatic frame crown a winner. The trick is to let the 4 windows talk to each other until one story stops fighting the others. Begin at the path. The updated orbit is the backbone. It tells you whether the object behaved like a mass being tugged by the sun, with slight corrections from vapor and dust. If the residuals shrink smoothly when October and December points are added, the spine is healthy. If a kink appears that the usual non-gravitational terms cannot soften, flag it with a quiet note and wait for independent fits to either agree or scold. This patience is not denial. It is a guard against errors that early reductions often carry. Move to the heartbeat. A clean brightness record is opinionated without being loud. If the curve rises toward perihelion and settles afterward with only small humps, the mood is calm. If there is a step during the Mars window that persists, ask whether rotating jets explain it. If there is a hump that fades, ask whether space weather lined up. Color indices and basic spectral lines can support either reading. They do not need to shout. They need to be consistent across instruments that saw the comet from different angles. Open the spectra. Water bands and simple carbon species belong. Traces of metals may appear. The question is not whether any nickel line exists. The question is strength relative to typical comets and whether multiple instruments saw the same ratios after proper corrections. One instrument can be fooled by calibration drift or an unhelpful sky background. 2 instruments on separate nights are less forgiving. If the lines look ordinary, the composition does not have to carry the plot. If the lines look unusual across platforms, composition earns a larger paragraph. Check the housekeeping. This is the quiet ledger that rumor ignores. Did instruments switch into targeted modes during the week of interest? Did pointing put the field where the ephemeris said it should be? Were there brief safe modes that explain a gap? Were there reprocessings that changed headers in a documented way? A responsible archive will let you trace the life of a file from raw packet to calibrated image. That trace is a dull thrill. It is also the difference between a story that will age well and a story that will wilt when the next batch lands. If any single window seems to shout on its own, try to make it sit with the others. A big non-gravitational push must be supported by an activity level in the light. A dramatic brightening must appear with a plausible color change or a rotation phase. A spectral claim that implies unusual dust must be mirrored by photometry that hints at altered grain populations. When pairs disagree, look for the boring fix first: clock errors, catalog choices, extinction, pipeline settings. The first fix that restores harmony is usually the right one. One possibility is that the entire puzzle will resolve into the quietest story. A comet from another system arrived. It outgassed in a way that textbooks would predict for the energy it absorbed. It passed the Sunday. It faded. If that is what the four windows show, we accept it with respect. A competing view suggests that the Mars week will hold a small twist that rewards attention, perhaps a brief surge, aligned with a solar disturbance or a new jet that woke as the sun found a seam. If that is what the four windows show, the twist becomes a paper that adds a paragraph to comet physics without touching the larger arc. It remains uncertain whether any result will rise to the level of a generational surprise. The ladder we built earlier is waiting either way. If an explanation tries to skip rungs, we count again and ask it to climb properly. If a signal candidate appears, we invite replication before we let the music swell. If a density claim leans too hard on an upper bound, we bring it back to the bracket that the images actually support. The discipline is not a brake on wonder. It is a belt that keeps wonder from flying off the ride. Every 3 parts we have returned to the same sentence. We are letting receipts outrun rumor. This is where that sentence pays off. When the lights return, do not ask for certainty first. Ask for coherence. Do the orbit, the light, the lines, and the logs prefer the same quiet answer? If they do, tell that answer well and enjoy the calm. If they do not, map the disagreement in public and invite help. Mystery that survives honest inspection is the best kind. It earns its own patience. There is one more thing to do before we close. Bring the audience back to the first image. Midnight, a shutdown, a silent week, a visitor passing a distant neighbor. The coincidence felt like a chord that begged for resolution. In the final part, we will resolve it honestly. Not with a flourish, but with a clear score that says what happened, what did not, and what questions deserve a front row seat the next time the universe drops a stranger at our door. Return to the clock. Midnight, October 1st. NASA goes quiet. Hours later, a visitor walks through the Martian neighborhood. Our story asked whether the silence and the passage were a duet or a coincidence. We now hold the shape of an answer. Shutdown rules produced silence. Space produced a rare geometry. The overlap created a mood that begged for drama. The receipts, the orbit, and the light, and the lines, and the logs are the tools that place mood below truth. If those receipts agree, the week becomes a lesson in how easily absence can feel like intent. If they argue, the argument carries dates and instruments rather than whispers. Either way, we end with a record that did not exist when the rumor began. The path remains the spine. A hyperbola fits the points from discovery through the reappearance. Non-gravitational terms, if needed, are small and behave like sunshine pushing vapor and dust. There is no bound loop. There is no shove that appears without a partner in the light. If the Mars week left any mark, it is a tiny improvement in the fit where the planet's gravity left a polite fingerprint. That is the kind of detail that orbit builders enjoy for its quiet beauty. It is also the kind of detail that will never trend, because it does not need adjectives, only numbers. The heartbeat confirms the ordinary grace of thermal physics. Brightness rose as distance fell. Modest humps may trace rotation in a jet, or they may trace a brush with solar weather. Color stayed within the family picture of comet dust, with short drifts that match the release of fine grains and a return as larger particles dominated again. If a step appears and persists, it reads like a patch that woke near the week in question and stayed awake. It is a fact to plot, not a character to assign motive. The second chance after conjunction makes this clear because the curve flows across the silence with no cliff, only a slope that textbooks could have sketched in advance. Spectra behave like good colleagues. Water features rise and fall. Simple carbon species appear as expected. Traces of metals may show, often faint, sometimes stronger on nights when geometry and grain size cooperate. Multiple instruments agree within the corrections that phase and calibration demand. If ratios wander, they wander inside the walls that comet studies built over decades. This tells us that metal in a mist remains a story about dust and heat, not about industry. It leaves room for surprise in future visitors, but it does not ask for a new physics here. Housekeeping logs close the loop. Instruments entered planned modes or safe modes and left again. Reprocessings are labeled with software builds and checksums. Gaps align with ground pass schedules and with common sense. Where a rumor imagined removal, a version history shows replacement by a cleaner product. Where a rumor imagined an unscheduled burn, a navigation update shows no impulse near the claimed hour, or it shows a routine event that the feed would have explained in any month without a funding lapse. The line from packet to product is not romantic. It is the romance of craft, a story told by engineers in plain clauses. One possibility remains open because humility keeps the door ajar. The archive may yet yield a recovery that shifts a parameter by a hair. A heliophysics plot may line up with a hump in a way that clarifies a brief dance between a shock and a coma. An amateur light curve may reveal a rotation phase that turns a blur into a map in time. None of these will overturn the spine. All of them will add grace notes to a composition that already plays. A competing view will always whisper that a grander secret could hide behind a rule or inside a closed sensor. Our reply is the same one we have built for 24 parts. Secrets that shape the sky cannot hide from many eyes for long. Orbits punish invention. Curves expose exaggeration. Spectra correct memory. Logs remember what people forget. The more watchers we enlist, the smaller the theatre for myth. That is not defiance. It is an invitation. Bring your lens, bring your code, bring your patience. We will meet you at the plot where numbers grow. So what did the coincidence mean? It meant that a procedural silence and a cosmic event overlapped for 7 days. It meant that a culture in love, with wonder, and wary of institutions, filled that overlap with stories. It meant we needed a way to turn mood into method. We built that way together. We climbed a ladder that placed quiet explanations first and left room for wilder ones, only if receipts demanded. The receipts did their work. The visitor kept going. The sky gave us another lesson in how ordinary processes, observed well, are a better spectacle than any suspicion voiced early. The next time a stranger crosses our yard, the playbook is ready. Pre-approve minimal status lines for public calm. Automate raw releases with clear labels. Rally the community into a shared notebook. Plot orbit, light, lines, and logs in 4 windows before anyone crowns a twist. If wonder survives that, it deserves a parade. If wonder folds into the ordinary, tell the ordinary well. Either path serves the same purpose. Curiosity becomes knowledge in public, and patience becomes part of the show.